Kids, okay. We're going to talk a little bit about path difference and constructive, destructive interference, in phase, out of phase, all of that good stuff. So let's say I have two waves like this. Hey, those two waves are in phase. When they're in phase, you get a bigger wave. You get constructive interference. If you're talking about light, that means it's a bright spot. If you have, okay, this, okay, these waves are out of phase. Out of phase is going to be destructive interference, which if you're talking about light, it's going to be dark right there. As far as our path differences go, if you are going from in phase to in phase, well, that means you have to be off the path difference, which most of the time we call delta L, is going to be equal to a multiple of a wavelength. Okay, so you have to be off by a multiple of a wavelength. Or if I was going out of phase to out of phase, same difference. So if it was out of phase to out of phase, again, my path difference has to be a multiple of a wavelength. Okay, whereas if I was going in phase to out of phase, okay, so if I'm going in phase to out of phase, then my path difference has to be off by a half a wavelength. And that should make sense because one of these waves has to get shifted by a half a wavelength. Well, how would that happen? Your path difference has to be off by a half a wavelength. So that your path difference would be off by a half a wavelength, or sometimes you'll see this written like this, where you do m plus a half, okay, where this is either 0, 1, 2, 3, whatever, so that you're always going to be off by a half a wavelength, okay, a multiple of a half a wavelength. Same thing if you're going to go from out of phase to in phase, then again my path difference has to be the same thing. I have to be off by a half a wavelength. Okay, so let's talk about an example where this could happen. Last year, and we have also talked about it this year, if you talk about a standing wave. So, for example, let's say I have, I don't know, the standing wave that's produced on a string. Okay, and if you're saying, this is the source of the wave, so the source. Okay, this is the thing that's going, if it's your hand shaking, and then let's say, hey, I want to find at this point right here. Okay, so we want to talk about starting here, going to there. So it's like, again, when you're doing this, you got to find your starting conditions, you got to find your ending conditions. So what are my starting conditions? So it's like, what are the two waves that are producing my pattern? So, well, that's my starting wave, is going to produce this interference pattern. And then the other is coming from bouncing off the fixed end. Well, when you bounce off a fixed end, it bounces back upside down. So my starting condition, okay, would be out of phase. Again, does that make sense? Again, will it always be out of phase? No, it depends on the problem. In this case, the two waves that make my interference pattern, this one, which is this one, and the one that's going down and bouncing off, which is this one, are out of phase to each other, okay? Because I decided I wanted to go to there, that means my ending condition is going to be in phase. Why in phase? Because it's a big wave, it's big amplitude, so I'm going from out of phase to in phase. Well, that means my path difference has to be off by a multiple of a half. I have to be off by a half a wavelength somehow. And if you think about this, if we do this, guys, my source is moving 1 1/4. So the source moved for L1, it moved 1.25 wavelengths. Again, 1 1/4. Okay. The reflected wave moved 1, 2, and 3/4. So 2 3/4. So L2 is 2 3/4. Okay, so again, 1, 2, and then bouncing back 3/4 of a wave. Well, then if you look at my path difference, so if I go this minus this, I get 1.5. Hey, look, that's a multiple of a half. So my path difference in this case would be 1.5 wavelengths. So, but hopefully that makes sense, or at least some semblance of sense. As far as finding starting, ending, path difference. Bye, kids.